So here we go. It's Thursday, November 19th, 2020. We're going to be looking at two-way tables, general addition rule, and Venn diagrams, and then one other thing about sample spaces. We'll get to the end. So first, we're going to talk about two-way tables and probability. When trying to determine probabilities involving two events, a two-way table can be used to display the sample space so the probability calculations are easier. It's an organization tool. For example, college statistics class wanted to find how common it is for young adults to have their ears pierced. They recorded data into variables, gender, and whether a student had their ears pierced. Okay. These are both categorical variables, going back to some of our earlier vocabulary. They did this for all 178 students in the class. The two-way table displays their data, right? Yeah. All right, so we have across the top, we have gender, male or female, and pierced ears, yes or no. Right, so we could do like marginal distributions, which we have in bold on the sides here, top on the side here, and the bottom here. We could do conditional distributions of male and female, of pierced ears or not. Right? We can do all these things that we've done previously. We're using this for probabilities now. Okay. So let's use this data to answer some questions. All right. Suppose we choose a student at random. What is the probability that the student has pierced ears? All right. Well, first, before we start, we're going to define two events using some letters here. We're going to have event A be defined as the person is male. Event B will be pierced ears. Right, so we have two events. We only need two events because the complement of each of these events is the other possibility. Right? The complement of being male is being female. Complement of pierced ears is not pierced ears. So we have all of the options covered with just two events here named. So in this first scenario, has pierced ears, right? We're calculating or determining the probability of event B. Right? So we're looking at pierced ears, yes. The total amount of people with pierced ears, 103. And we have a total number of students of 178. So the probability of having pierced ears in this class is 103 out of 178. Okay. So the two-way table just allows us to easily have the data organized. So I can just pick the numbers that I need. Okay. Part B here we have is male and has pierced ears. This is important. We're looking at the and scenario. So I'm calculating or determining the probability of A and B. So I'm looking at the male column here and yes to pierced ears. The number of people that are male and have pierced ears is just the 19. So we have 19 out of 178. Are there any questions so far? So then our last scenario here we have is male or has pierced ears. So this will be P of A or B. So they can be male and satisfy this scenario, or They can have pierced ears and satisfy this scenario. So we have 103 people that are having pierced ears. We have 90 people that are male. That equals 193. That's impossible. I only have 178 people. So what went wrong? Why did just adding those two totals not work out?
Don't we need to subtract the number of males who have pierced ears? Because now we count them twice, right?
Yes, Yusuf and Brian in the chat, yes. We counted those people twice. We counted them in the amount of people who have pierced ears, and we counted them in the males, right? So when there's this intersection of the two, we can't just add the probability of both things when we have that or situation. We have to subtract the thing that got counted twice. So that's exactly what we'll do. We'll say 193 minus 19. And that gives us 174, right? Which makes more sense. It's less than our total. It is possible, right? So we have 174 out of 178. We could also determine this by just adding everything within that part, right? Male with pierced ears, male without pierced ears, females with pierced ears. The only number we're excluding is that 4 that is neither of the two situations. All right. Excellent. Thank you, Yusuf and Brian. Any questions, comments, concerns, clarification? All right. Does anyone need a moment to write any of this down? Okay. So then this leads us to exactly what was just pointed out by Yusuf and Brian, right? We double counted the outcomes when we did probability of A plus probability of B. Right? We counted that probability of A and B 2 times. Oops, mistake. So that leads to the general addition rule for 2 events. This is different than the addition rule for disjoint or mutually exclusive events that we saw on Tuesday. If A and B are any 2 events resulting from some chance process, then probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Right, so we have to make that adjustment for the things that have been double counted. Right. The addition rule for mutually exclusive events is just a special case of the general addition rule for 2 events. When events A and B are disjoint, then the probability of A and B equals 0, which is again a scenario that we saw on Tuesday's class. And you're left with the probability of A plus the probability of B. So if you're going to remember one of the rules about addition rule for 2 events, you want this one because it accounts for all the scenarios. Right? The addition rule for mutually exclusive only applies to mutually exclusive or disjoint events. All right. Is there anything I can clarify or explain better or another way? All right. And if you need a moment to write anything down from this slide, can you raise your hand? Now, let's consider Venn diagrams. Two-way tables are one way to illustrate the sample space of a chance process involving two events. Another way is to use Venn diagrams. Venn diagrams are used in other branches of mathematics, set theory to name one, and some standard notation and vocabulary have been developed. So we're going to do some of that right now with some pictures. That's kind of nice. Complement. This was introduced on Tuesday's class. If A is an event, then the outcomes not in A are A complement, or A superscript C. This is a common notation in probability, but also in other areas of mathematics, to use that superscript C to refer to the complement of an event or of a set of outcomes. All right, so in this case, the box here represents the sample space. A is our event. Everything outside of A is a complement. Does anyone need a moment to write this down or draw the picture? Then we have mutually exclusive or disjoint. Again, this was introduced on Tuesday's class. If A and B are two events with no outcomes in common, then they are mutually exclusive or disjoint. In the illustration, the events do not overlap. Pardon me. So again, the rectangle here, the large rectangle, is the sample space, represented with S. We have event A, we have event B. They do not overlap. They have no outcomes in common. These two events are mutually exclusive. One cannot happen and the other one at the same time. We can't have both things occurring. Okay. Can you raise your hand if you need a moment to write this down or draw the picture? Next, this is a new term, intersection. If A and B are two events with some outcomes in common, then they have an intersection. This intersection is the event A and B. In the illustration, the shaded area represents the intersection. Corresponding notation is A, this little like arch looking thing, which we just read as intersection, B, or we can say A and B. So the part that overlaps between the two events A and B is the intersection of A and B. It is the outcomes that they have in common. Does anyone want a little bit of time to write this down or draw the picture? Please raise your hand. Our last new term here is union. If A and B are two events in a sample space, the union is the outcomes of both events. This union is event A or B. In the illustration, the shaded area represents the union. The corresponding notation is A, U. looks like a little U, B. And we read that A union B or A or B. Okay, and we see that as everything between A and B is part of the union. We put it all together. Right? It's like a marriage. With what belongs to A belongs to B now, what belongs to B belongs to A now. The union. Right? And once again, if you would like a moment to write this down or draw the picture, please raise your hand. Okay. So now, let's revisit our pierced ear data from earlier, along with a Venn diagram of the same event. In this case, we're only looking at the data without the totals. We will just recall that we have a total of 178 people. Right? So, we're going to find the following counts and probabilities. So our first one, A and B. The intersection between event A and B. We solved this earlier. There are 19 people who are male and have their ears pierced. That's A and B, which gave us the probability 19 out of 178. Right, and we see that, right, as this here, it is the intersection in our Venn diagram of the events, the shared outcomes. We also have it right here. So then we have A and B complement. So in this case, we want to know what is in A and in the complement of B, which means what's in A and what is not in B. All right. So we know that in A is this yellow circle, but we have to exclude the 19 because that's in B, and I can't consider anything that's in B. I have to only use the complement. Okay, so that leaves us with this like most of this thing here, right? But we have to cut out the intersection, right? So we can essentially draw it poorly like this, right? So we get that. The other part of the data that's not in B is the 4 over here, but it's also not in A, so we can't count it because it must be in A and not in B. So that leaves us with just the 71. So our probability is 71 out of 178. So any questions or anything I can clarify about that one? All right, so then next we have A complement in B. If we're looking at A complement, we need to look at everything that is not in A. Right, so that includes the 84 from B that's not in A. Right, so again, leaving out that 19. Right, and considering everything in B, not in A. And again, we have this little 4 over here. However, that 4 is not in B as well, so it can't be counted. So that leaves us with just the 84, right? The 84 that is not in A, so it is female, right? I'm sorry, what is A? Yeah. A complement, so A was being male, so A complement is being female, and event B is pierced ears. So female and pierced ears, that's the only one that works. Okay, so we have 84. So our probability is 84 out of 178. Right. Essentially, each of these is going through one of those four numbers that's available. You want to think about it that way. Right. This number, the 71, is A and no, male and no, male and yes, female and yes. Last one, female and no. A complement and B complement. Right. Not in A and also not in B. That leaves just our little 4 over here. Not part of the A, and it's not part of set B. So we're at 4 out of 178. All right. Any questions? Anything I can clarify about this? All right. So last thing is not on the PowerPoint. And this to these. All right. We need to do this example because you need to understand this to answer one of the questions on the quiz for this week. So this scenario, we're going to be creating a sample space to represent a choice process. Right, so our context here, we have 6 friends, Allison, Bree, Ella, and Francisco, and they are the finalists for a prize drawing. The prize is 2 tickets to a concert. 2 of them will be selected at random as the winners. What are the chances that Bree and Francisco are selected? Right? In order to solve this, we need to create a sample space that illustrates all the possible outcomes of choosing 2 people from that set of 6 people. All right. So the best thing we can do is, instead of using the names, right, we can use like the first letter of all of their names to create our sample space. So that means we'll have A would be Allison, B would be Bree, C is Chuck, D is Dan, E and F. I did this on purpose so they all had different letters to start their name. So we just systematically go through and pair these things up, right? The order in which they're paired doesn't matter. A and B paired together is the same as pairing B and A. All right, so I just need to go through and just sort them out. So I go, well, we can have AB, AC, AD, AE, and AF. All right. Then I'll start with B. We can have BC. I already had AB, so I don't need to do BA. BC, BD, BE, BF, CD, CE, CF, DE, DF, and lastly we have EF. I do this in this order because it does do that kind of like shrinking down in size. Each next row has one less thing than the previous row when I do it this way. So that's why I specifically write it this way when I create my sample space. I don't skip things this way. So then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 equally likely outcomes. Right? We want B and F. Right? And this is the outcome we're looking for. there is only one option. There's not another way for B and F to be selected. So that means the probability, right, of this event is 1 out of 15. That's it. And so this is another way of creating a sample space that represents this choice process. This has to do with all the events being equally likely to happen, all these outcomes, and that order doesn't matter. We create more possibilities of the outcome if the order does matter. That comes later. Are there any questions about this process? So then, looking at our module, the CYU for this week. Here's just some information. This is not part of the quiz. These are just things that we've covered. There's a question having to do with using a relative frequency table to determine a probability. The numbers listed up here is the probability of each of the outcomes individually. So a two-way table problem. This is like the choice process we just did, this type of problem right here. And this has to do with understanding that new notation and mutually exclusive events. There are just multiple choice. There is no typing of an answer or anything, so it should be relatively straightforward. And lastly, the discussion board for today. It involves making a two-way table to demonstrate this event. Oh, I hit the wrong button. So we have a standard deck of playing cards with jokers removed. Consists of 52 cards in 4 suits: clubs, diamonds, hearts, and spades. Each suit has 13 cards with denominations ace. I'm a numbnut. Sorry, guys. The 1 shouldn't be there. I'll fix that later. Ace, 2, 3, 4, 5, 6, 7, 9, 10, Jack, Queen, King. The Jack, Queen, King are referred to as face cards. Imagine that we shuffle the deck thoroughly and deal 1 card with defined events. F is getting a face card. H is getting a heart. All right. So in your two-way table, you could have like the top title be face card. You're getting a face card, yes or no. And the row titles be getting a heart, yes or no. And you fill in your totals accordingly. All right. That would be for making the table, two-way table. Find the probability of F and H occurring, getting a face card, and that it's a heart. And then explain why probability of F or H is not equal to probability of F plus probability of H. Then use the general addition rule to find P of F or H. Okay, so the largest part of the work in this one is creating that two-way table.